Hello, today's lesson looks at the principle of least action, which lies at the heart of an alternative formulation of mechanics which was developed by Euler, Lagrange and Hamilton about 150 years after the work of Newton. Consider a particle moving freely under the influence of a gravitational force. If the particle begins at some location x1 at time t1 and ends at some different location x2 at time t2, is it possible to determine the exact path that the particle takes between these 2 points? Well, it turns out that there is a way of doing this. If we consider a variety of such paths, for example, we might consider this path, and we could consider an alternative path which looks like this. We could consider a path that even looks like this. In fact, we could consider all possible paths. And then for each path, if we calculate the difference between the kinetic energy and the potential energy at each point along the path, and then add up all of these contributions to get a final number, we find that the path for which this final number is least is the path that the particle actually takes. We can formalize this by defining something called the action, S. And the action is defined as the time integral from t1 to t2 of the difference between the kinetic energy and the potential energy. And it is this action principle which lies at the heart of this alternative formulation of mechanics. We are interested in finding the path for which S is least. So how do we do this? Do we have to calculate S for every possible path and then compare values? Well, thankfully no, as this would require quite a lot of effort. Instead, we can make use of what we know from calculus, and in particular what we know about the minima of functions. If we consider a function f of x of a single variable x, then one way of knowing whether we are located at the x value which corresponds to the minimum of f of x, and I've located that position x min, is to take a small step away from this x value and see what effect this has on the value of the function. So if we have a function f of x, and then we move away from x by some small amount, epsilon, then clearly making this shift in x is going to have an effect on the function. F of x is going to change to f of x plus epsilon. Now, if epsilon is small, we can expand this function as a Taylor series. If you're not familiar with Taylor series, then I would suggest you look at my video on Taylor series. But I'm going to assume for now that you do know how to Taylor series expand this function. And therefore we can write f of x plus epsilon equals f of x plus epsilon df by dx plus epsilon squared d2f by dx squared plus, and so on. We then see that the change in f is going to be equal to the shifted function f of x plus epsilon minus the unshifted function f of x. For f of x plus epsilon we can insert the expansion here, and therefore we're going to have f of x plus epsilon df by dx plus epsilon squared d2f by dx squared plus, or the higher order terms, minus f of x. And we see that the f of x's cancel, and therefore we have that the change in f is going to be equal to epsilon df by dx plus epsilon squared d2f by dx squared plus higher order terms. Now, if we're at the minimum of f of x, then clearly the gradient at this point is 0. And so at the min, we know that df by dx equals 0. And so we see that this term is going to be 0, and therefore our change in f is going to be equal to epsilon squared d2f by dx squared plus higher order terms. And so we see at a minimum, if we make a small change in our x position, then our function changes at second order in the small step change. So delta f changes to second order epsilon squared. And so we can summarize this by saying that at the minimum of a single valued function, the change in f is equal to 0 to first order in epsilon. In other words, f of x plus epsilon minus f of x is equal to 0 to first order in epsilon. So if you take a small step away from the minimum of a function, it makes no difference to the value of the function to first order in epsilon. Now it's important to realize that we are not dealing with a function of a single variable and trying to find the minimum of a function. The minimum of a function is a task in trying to find a single number which represents the point where the function is least. Rather, in our case, what we're trying to do is find an entire path for which the action is least. And so we need to use a slightly different approach. This is a branch of mathematics called the calculus of variations. But the general gist is the same. So, for example, if we imagine the actual path being represented by the function x of t, so this is representing a particle moving from position x1 at t1 to position x2 at t2, and this represents our actual path, then what we want to do is look at some small deviation away from the actual path. And then our hope is that if we then look at the change in the action as a result of that small deviation away from the actual path, then that change in the action should be 0 to first order in the change of the path parameter. So let's make this a little bit more explicit. Imagine that I deviate the actual path by some small amount, like this. So what we're going to do is imagine that for each different t value, the path has been changed by an amount, and that amount's going to be eta of t. And therefore we can say that for the dashed line path, rather than having x of t, we've now got x of t plus eta of t. And this represents our deviated path, this represents our actual path. Now recall that our action s is defined as the time integral from t1 to t2 of the difference between the kinetic energy and the potential energy. And so now what we want to do is actually ground this in a particular specific example. So we're going to consider a particle moving in one dimension in a potential v of x. And so our action is going to be written in this example as being the integral from t1 to t2 of half m dx by dt squared. So this is just the kinetic energy, half mv squared. So this is a particle moving in one dimension, minus the potential energy, which we're going to assume is just v of x. And we want to integrate this with respect to time. Now the idea is simple. What we're going to do is look at how the action changes as a result of the small deviation in the actual path x of t. And then we're going to look at the difference between the actual path action and the deviated path action. And if the original path x of t is actually the original path, then that variation delta s should be equal to 0 to first order in eta. So we're going to look at delta s, which will be equal to s of x plus eta minus s of x. And if s of x is actually representing the real path, then this should be equal to 0 at first order in eta. So this is the analogue of saying for a function of a single variable, if we're at the minimum and we take a step away from the minimum x position, then to first order in that step parameter, there should be no change in the value of the function. So now this is just a question of putting in these values into this expression. So the first thing we're going to do is we're going to look at what s of x plus eta is. So s of x plus eta, well, that's going to just be a case of wherever we see x in this expression here, replacing it with x plus eta. So that's going to be the integral from t1 to t2 of half times m bracket, and we've got d by dt of x plus eta, close bracket squared, minus v of x plus eta dt. And so now what we can do is we can expand out this bracket. That's going to give integral from t1 to t2 of half m, well, this is going to be dx by dt plus d eta by dt squared minus v of x plus eta dt. Next, we would like to expand out the square term. So that's going to give us dx by dt plus d eta by dt all squared is equal to dx by dt all squared plus d eta by dt all squared plus the cross term, which is 2 times dx by dt times d eta by dt. Now, because we're interested in the requirement that the change in our action is 0 to first order in eta, we can ignore the higher order eta terms. And this is a second order eta term, so we can ignore that. Secondly, we would like to expand out our potential energy function as a Taylor series, and so we can write that as v x plus eta equals v of x plus eta dv by dx plus eta squared over 2 factorial d2v by dx squared, and so on. And again, we're only going to consider the first order eta term and ignore any higher order eta terms. If we now substitute these results back into our expression, we have that s of x plus eta equals, now I'm going to write this in a slightly different form. I'm going to write half m dx by dt squared minus v of x, so that minus, and then I'm going to put the v of x here, minus v of x, and then we're going to have a plus half m times bracket 2 dx by dt d eta by dt. So that comes from this term being multiplied by half m, and then we're going to have a minus eta dv by dx, and this term is just this term, and the minus sign comes from here. And then we've got plus higher order terms in eta, and all of that is being integrated with respect to time. Now, we are interested in the change in the action. Remember, we want delta s, which is equal to s of x plus eta minus s of x, to be equal to 0. Well, we've just written down an expression for s of x plus eta. We know that s of x is just the original expression, which was the kinetic energy term minus the potential energy term. So if we substitute our original expression, we're going to have the integral from t1 to t2 of, well, now we've got this expression, but notice when we subtract our original action is s of x equals integral t1 to t2 times half m dx by dt squared minus v of x dt. That was our original action. So notice when we substitute our original action from our shifted action, this term here is going to exactly cancel this term here. So these two terms will cancel, and what we'll be left with is these two terms. And so delta s is going to be equal to, well, this term, we see that the half and the 2 cancel, so we're going to have m dx by dt d eta by dt minus eta dv by dx, and this is being integrated with respect to time, and we require this to be equal to 0. So let's now think about how we can ensure that this is equal to 0. So we want to ensure that this integral is equal to 0. At the moment we don't know what x actually is. However, we do know that whatever eta is, this integral still needs to be equal to 0. We have a slight problem at the moment because in the first term we see that eta is being differentiated with respect to time, whereas in the second term it's not. In the second term, eta is just simply multiplying dv by dx. So ideally what we want to do is to factor out eta in this expression. So we need to address this first term, and in particular we need to integrate by parts. So how are we going to do that? Well, firstly, notice that if we write d by dt of dx by dt multiplied by eta, in other words, if we differentiate this product, and the product is dx by dt multiplied by eta, then we can use the product rule to write this as d2x by dt squared multiplied by eta plus dx by dt multiplied by d eta by dt. Then what we can do is we can rearrange this expression so that we have dx by dt d eta by dt equals, well, that's going to be equal to d by dt dx by dt eta minus d2x by dt squared multiplied by eta. So I've just rearranged this expression to get this expression. Next, if we integrate both sides with respect to time, so if we integrate from t1 to t2, dx by dt multiplied by d eta by dt, that's going to be the integral from t1 to t2 of d by dt bracket dx by dt eta dt minus the integral from t1 to t2 of d2x by dt squared eta dt. Now let's pay attention to this term here, because this term here, as you can see, we have some object which we're differentiating with respect to t, and then we're integrating it with respect to t. Now, integration and differentiation are the inverses of one another. So if we differentiate and then integrate, the integration is going to undo the differentiation, and we're going to just be left with this term evaluated at t1 and t2. So this is simply dx by dt eta evaluated at t1 and t2. Now, if you recall our original diagram where we had x and t, and we were considering the actual path of motion between t1 and t2, we were then considering a deviated path, and the deviation away from the actual path was being represented by our function eta of t. Clearly, at t1 at the start point and at t2 at the end point, the variation away from the actual path is 0. And so we can see from this diagram that eta of t1 equals eta of t2, and that is equal to 0. This is just saying that there is no deviation away from the actual path at the start point and at the end point. This statement here tells us, therefore, that this term is equal to 0, because this term involves evaluating eta at t2, which is 0, and evaluating eta at t1, which is 0. And so we can get rid of this term. And so why have we done this? We've done this because this is telling us that the integral from t1 to t2 of dx by dt d eta by dt is equal to minus the integral from t1 to t2 of d2x dt squared multiplied by eta. So we see that eta is no longer being acted on, it's no longer being differentiated. So we can replace this term with this term. And if you notice, this term here is precisely this term here. And so this process has allowed us to rewrite this expression in a form where eta is not being acted upon. So let's now substitute this into this expression. We have just seen that it's possible to use integration by parts to rewrite this expression in this form. And so now what we're going to do is substitute this back into our varied action. So delta S is equal to the integral from t1 to t2 of minus m d2x by dt squared eta minus dv by dx eta dt. And so we have managed to rewrite our expression for delta S in a form where eta is not being acted upon by anything in either term. And so now what we can do is we can factor out eta. So we can write delta S is equal to the integral t1 to t2 of minus m d2x by dt squared minus dv by dx multiplied by eta dt, and we require this whole expression to be equal to 0. Now this places a condition on the thing inside the square bracket. For this integral to be equal to 0, we require that the thing inside the square bracket must be equal to 0. And so this constraint can be written minus m d2x by dt squared minus dv by dx equals 0. And if we rewrite this, we can write it as minus dv by dx equals m d2x by dt squared. Now you might recognize this expression. On the right hand side we have the mass times d2x by dt squared, and this term is simply the rate of change of displacement with respect to time, which is the acceleration. And so we see we have mass times acceleration on the right hand side. What about the left hand side? Well, here we have the negative gradient of the potential energy function, which, as you know, is the force F. And so we see we have recovered Newton's second law. We have demonstrated that the principle of least action gives the right answer. It says that the path that has minimum action is the one satisfying Newton's second law. Now, I don't know about you, but I find this remarkable. It's worth ending with a few remarks. We've been referring to the principle of least action and talking about the action being a minimum. However, it doesn't have to be a minimum. What we really mean by least is that the first order change in the value of the action is 0 when we change the path. So it would be more accurate to refer to this as the principle of stationary action. Either way, this approach to mechanics is both elegant and powerful, and it lies at the heart of our modern formulation of quantum field theory and the standard model of particle physics. I hope you've enjoyed this short introduction to a fascinating topic.